This might get a little confusing. Okay, I want you to think about how you live right now. Or better yet, how you're watching this very video. Are you lying down in your bed with your laptop or waiting for a friend outside and watching this on your phone? You know what? Let's break that down and take a look at your life. Okay, so a phone bill is approximately $60 every single month, which means roughly $2 a day. Now, if you're paying $2 every single day on your phone bill, that means you have a little bit more money to splurge on more urgent things. Now, one adult spends roughly $300 on food every single month. That's about $10 a day. Every single person spends $2 on toilet services every month, and every single person spends $125 on gas for their cars each month, expanding to about $4 for gas every day. Now, these are just four aspects to our everyday lives. We still haven't considered education, other modes of transportation, eating out, paying bills, maintaining your home, or even having access to the internet. Now, with an average salary of $200 every single day, people can earn these nice facilities and so much more. But let's take a step back. Let's say that you earned $2 every single day. Yep, a massive jump. Now, you wouldn't be able to afford a phone because, well, $2 is your whole day's salary. If the average cost for food is $10 every day, you'd be living off 1/5 of that. Now, you might be able to afford a toilet service, but the installation of one is highly unlikely where you live. And your mode of transportation would, well, be your feet. Now, what if I told you that 9.2% of our world, that means 689 million people, actually still live like this? And because of the pandemic, 8% more of people will go into this state. This doubles the amount of people we have living without access to food, a connection to the external world, or even access to healthcare and a doctor by their side. Now, I looked really deep into this issue and wrote an entire review paper on how quantum dots can be used in point of care and rapid testing. Check it out in the description box below. Now, this advancement actually uses nanotechnology, and I can go on and on about the steps of how these nanosensors actually work, but I'm going to give you a really deep dive on quantum dots on the molecular level and how they actually work with their quantum mechanics, chemistry, and all the math surrounding these itty bitty electrons. Now, nanotech actually manipulates materials on the nano scale, and because every single material is investigated at the nanoscale, they become really small, changing their properties such as reactivity, conductivity, and solubility as a function of the particle size. Especially because on the nanoscale, the Coulombic attraction between the protons and the electrons actually increases, and this plays a huge role in the behavior of different nanomaterials. Now, what's really special about nanosensors is that they can detect problems well before so many other outdated methods. And the reason behind this is because all the first signs of really any disease occur at the nanometric scale. Now, nanosensors can actually detect multiple different targets in the same reaction, so they can test for basically any diseases all at once. They can do this really efficiently and quickly. In 2009, we actually had the influenza flu breakout. It would normally take us 14 days to know if you had the flu, but with nanotech, you could determine the pathogen within 3.5 hours. I mean, that's just crazy. Now, within nanotech, we have nanoparticles known as quantum dots. These are artificial semiconductors that basically transport electrons, and because they're so small, the quantum effects come into play. Now, when UV light hits these nanoparticles, they can emit different colors of light depending on the electron wavelength, and this all relates back to their size and their shape. So, by controlling the size, the particles can emit or absorb specific wavelengths of light, and this results in different colors being emitted. Now, these properties of quantum dots all depend on their size, shape, composition, structure, and material. One example is where we can control the emission wavelength by tuning their size. Smaller QDs with a radius of about 2 to 3 nanometers emit shorter wavelengths, and they generate cooler colors like violet, blue, and green. On the other hand, larger quantum dots with a radius of about 5 to 6 nanometers emit longer wavelengths and generate warmer colors like red, orange, and yellow. Now, what's really cool about quantum dots is one of their subsets, known as graphene quantum dots, or GQDs. Well, judging by the name, you can see that GQDs contain graphene, which is basically an unrolled form of carbon nanotubes, and these have great potential within biosensing because of their photoluminescent properties. Now, the GQDs emit different colors just like quantum dots because of their PL properties, which rely on the band gap and the size, and these are one of the outcomes of these super strong quantum properties that GQDs possess. Now, GQDs can have many different functional groups to hold different drugs or biomarkers, and can also bind with aromatic molecules through electrostatic bonding. Now, this is known as pi-pi stacking. This is just basically non-contact forces, where you have push and pull forces, but they don't touch. Now, to truly understand this pi-pi stacking, you have to understand spin polarization, which occurs on a molecular level in GQDs. Now, graphene is a bidimensional material, and it basically has a honeycomb-like structure arranged in sp2 bonded carbon atoms. Now, sp2 bonds are basically a result of mixing one s orbital and two p orbitals. Each of the carbon atoms are then attached to three other carbon atoms, making these three bonds. Now, the sp2 hybridization is basically where the p orbitals are held together through pi-pi stacking, and that's basically where this all comes together. Now, because of these bonds, these nanoparticles can actually cross biological barriers that are typically not accessible to really any particles. Now, all of these bonds and their configurations affect something known as the quantum confinement effect, and all these effects lead to spin polarization. But before we get into all this, we also have to learn about absorption peaks. Now, the absorption is basically just a measure of the amount of light that is being absorbed, so the higher the value, the more of a specific wavelength is actually being absorbed. Now, the GQD absorption peaks are actually comparable to other graphene-based materials, but we have to look at multiple properties to do so. The properties include the sp2 hybridization configurations, the functional groups, and the synthesis methods. Now, the dimension of the GQDs is comparable to the exciton diameter, which is basically the distance between electrons and holes. These particles are treated as particles in a box because of their bandgap energy and is actually inversely proportional to the size of the potential well. A single aromatic ring, also known as benzene, has a bandgap of 4 electron volts. When increasing the number of these aromatic rings, there's a reduction in the energy gap. So for example, graphene oxide with 20 aromatic rings can have a bandgap energy of 2 electron volts. But with 100 rings and a size of 3 nanometers, it'll have an energy bandgap of 0.5 electron volts. Now, all of these properties actually relate to something known as the quantum confinement effect. And when these properties change, the quantum confinement effect also changes. And it's basically just really important to understand the overall umbrella of quantum dots. Now, the quantum confinement effect is always observed when the particle size is way too small to be comparable to the actual wavelength of the electron, which is basically all quantum dots. Now, I keep mentioning something known as the bandgap energy, and this is because the quantum confinement effect highly relies on this. Now, the bandgap is basically the minimum energy that is required to excite an electron from its ground state, known as the valence energy band, onto its other state, known as the conduction band. Now, basically, the presence of all these multiple atoms can cause splitting in its electrons when they're grouped, and this forms these different energy bands. So the most filled band is known as the valence band, which basically has lower energy levels, but the most empty band is known as the conduction band, which has a lot of higher energy levels. Now, the valence and conduction band are basically forbidden by an energy gap, known as the band gap. Now, when the holes and electrons attract, they create a bound state, which occurs when the particle basically can't travel to infinity and is confined to a potential well. Now, in quantum dots, the excitons are actually confined to a much smaller volume of quantum dots, and this results in a lot less splitting of the energy bands, which doesn't result in as much of the quantum confinement effect. Now, all of these effect theories and mechanisms also all relate to something known as the particle in a box theory. Now, this is known as an infinite potential well, and it basically describes the particle's free ability to move in small spaces with different barriers that they cannot go through. These particles also occupy different positive energy levels, and the exciton diameter are isolated by the bound state, and they can be measured through this very confusing yet cool equation. Now, the H actually represents Planck's constant, which relates to the energy of one quantum, or photon, of electromagnetic radiation to the frequency of that radiation. M represents the mass of the particle, and L is the length of the box. This equation actually proves that quantum dots and electrons can occupy certain discrete energy levels, which is why they are called artificial atoms. As a whole, the particle in a box theory is an application of Schrödinger's equation. This equation describes how any physical system, when subjected to certain forces, can and will change over time. This is why in certain situations, electrons act as particles, but in others they act like waves. Now we know that the particle is somewhere in that potential well, we just don't really know until we measure it, exactly where it is. And this is almost like superposition in quantum. You can check out my review paper to see what we can actually do when we harness these quantum dots for point of care and rapid testing, and how we can basically remodel the entire healthcare system with these quantum dots.